Okay, hello everybody. I've been looking forward to this opportunity for quite a long time because I've become very interested in the foundations of projective geometry. I think it's really fascinating because, we have the Elements, this great book by Euclid, which sets out some axioms and helps us understand how everyday space can be thought of. But projective geometry is much more fundamental. And the axioms behind it are actually quite a lot simpler in many ways. And so I spent a long time trying to understand the thing visually and learning theorems and stuff. But what I'm starting to find really fun is converting the sort of wordy axioms given in particular by Coxter in his wonderful book on projective geometry, and converting them into more set theoretic concepts. Basically, if you want, I like to take the geometry out of projective geometry. What I mean is this, right? One of the most beautiful things about two-dimensional projective geometry is that points and lines are logically basically equivalent. They have identical properties in the sense that every pair of distinct points defines a line, and every pair of distinct lines defines a point where they meet. We don't have such a notion as parallel lines that never meet. In projective geometry, on the extended Euclidean plane, say, you'd imagine perhaps parallel lines meeting at infinity. Anyway, we insist that every pair of lines meets at a single point, and that there is a single line joining every pair of points. And because of that, and the other axioms that we choose, basically, points and lines are symmetric. So I thought, well, why don't we rewrite the axioms of projective geometry so that we don't even talk about points and lines? Why even bother mentioning them? So I've done this. I don't claim to be an expert on previous writings on the foundations of projective geometry. I know that Von Staudt did some excellent work. I know that Whitehead did a fantastic job of axiomatizing projective geometry using the ideas of collinearity. So I don't know if what I'm going to present here is a new thing, but it's new as far as I know, and I think it's very exciting because it seems to reveal a lot of new connections and perhaps some new sort of fundamental objects which are playing big parts in projective geometry, which are harder to see if you only look at it on a kind of purely sort of geometric point and line kind of perspective. So anyway, here's the idea. We have a set. Okay? I have a set, I call it E, with a little scripty thing, and it's partitioned into two disjoint subsets. One of them would represent the set of points, and one of them would represent the set of lines. So maybe E minus 1 is the set of points, and maybe E1 is the set of lines. Or maybe E minus 1 is the set of lines, and E1 is the set of points. It doesn't matter because these two things have symmetric roles throughout the theory. So I might sometimes get a bit confused about which one's which, but don't worry. The point here is that we're not going to ever use these words points and lines really when we're making our definitions. All that matters is that we have this set, and it's bipartitioned into two disjoint subsets, one of which we might call the elements of one of which lines, we might call the elements of the other thing points. Okay? So a set of elements partitioned into two different types, which we might call points and lines. So it doesn't matter which of these ones you want to call points and which ones you want to call lines, because the logic is symmetric. Okay, now let's touch with reality. Good old reality. This is how it might work in practice. Let's say we want to let e minus 1 represent the points, and we have this kind of figure here. And let's say that e1 represents the points. So this figure here might look like this, might be drawn like this. Now there's one other sort of fundamental idea, really fundamental idea that we need to do this kind of geometry, and it's the idea of what you might call the point, or sorry, the meet or the join of a pair of elements. So you see there I've written that, I'm trying to read this text, it's being laterally inverted by the camera, it's a bit difficult. You see this point little a is written as capital A dot B. Okay, so what does capital A dot capital B mean? It means the meet or join of capital A and capital B. Essentially, it means little a is the line connecting big A and big B. So here's the point, right? Let's get to the actual definition. For any m can either be 1 or minus 1. Let's say we've got a pair of elements in e to the m. So essentially we have a pair of elements of the same type. Maybe they're points, maybe they're lines. That depends on the value of m, whether it's 1 or minus 1. Now, we're going to insist that this thing here, which we call alpha dot beta, or maybe we'll call it alpha beta, or maybe we'll call it alpha meet beta, or maybe we'll call it alpha join meter. We've got plenty of names for it. But basically, it's an element of the opposite type. And it's essentially, if you like, the element which sort of links alpha and beta. So if alpha and beta were lines, then alpha dot beta would be the point where these two lines intersect. If alpha and beta were points, then alpha dot beta would be the... If alpha and beta were points, then alpha dot beta would be the line through them. Okay? So there we go. So now let's get back to our diagram. And you can see it working out, look. There's our line alpha, and we're writing it as move over here. Okay, there's our line A, and we're little a, and we're writing it as capital A dot capital B, because it's this line which goes through capital A and capital B. We've got that capital B, that's this point here, well, that lies on the intersection of line little a here and line little c here, and so forth. So this is the basic idea of how we write when two elements of one type are going to be somehow joined or linked by an element of the opposite type. Okay, so when you're thinking about these kind of joinings or linkings, you're essentially thinking about having two separate objects and then getting a third object which somehow relates those two things. That's one way to think about space and stuff. Another way, which is kind of nice, is to think about neighbourhoods. This is often done in topology. What's the set of things close to something? And in projective geometry, it's nice to think, well, the way I think of neighbourhoods is when people start talking about ranges and pencils. So a range is the set of points on a line. Okay, so if you have a line and it's got all the points dot 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 on it, then the range of that line is just the set of points on the line. And the pencil of a point is just the set of all lines that goes through that point. It's the kind of dual notion. Well, I prefer to call both of these things neighbourhoods. So I'd say that the neighbourhood of an element is basically the set of all things, in a way, which the set of all things of the opposite type, which are touching it. But okay, we want to get away from points and line talk and get into some algebra. So here's a sort of algebraic definition of a neighbourhood then. Let's, I'll fold that bottom bit down temporarily. Okay, so once again, we'll suppose that m could be -1 or 1. It doesn't matter if we're going to talk about points or lines. But we're going to suppose that we've got this element, alpha. Maybe it's a point, maybe it's a line. It belongs to this set EM. So it's of type M, whatever. What's its neighbourhood? Well, its neighbourhood is defined as the set of all joins that alpha has with other elements of the same type. Okay? I think this is a kind of neat way of defining a neighbourhood because it works for both lines and pencils. So let's look at an example, okay? Suppose, suppose alpha is this line here. Well, alpha is a line. We want to calculate the neighbourhood of alpha. That ideally should be the set of all points on that line. How do we find them? Well, let's look at the collection of all other lines, of all other elements of the same type. And since every pair of lines intersects at one place, we can define the neighbourhood of alpha to just be equal to the set of places where we have these intersections. So there's a point where alpha intersects with this first dotted line beta 1. There's another point on the neighbourhood of alpha where it intersects with the line beta 2, and there's a third point here coming from getting cut by beta 3. Now, the skeptical amongst you might ask, well, is this a decent definition for the range of points on a line? What happens, for example, if there are no other lines? Well, that doesn't happen under our axiomatic system. We always insist upon the existence, essentially, what it boils down to is we always insist upon the existence of at least 4 points and at least 4 lines. And since every pair of lines will cross and every pair of points has a line between them, basically that means that you don't get lines that have no points on them and things like that. Not in the two-dimensional case, which we're focusing upon. We're focusing on purely 2D projective plane, projective geometry here. Okay then, so that's the basics of how we think about objects being close to each other. And there's basically just 2 other little pieces of mathematical machinery that we need to introduce in order to be able to give these axioms of projective geometry in a really kind of tight way without having to talk about points and lines and all the rest of it. So I don't know which one to talk about first. Okay, let me get this idea out of the way, because I think this is quite a powerful idea, and I think hopefully it might even be novel. It seems to make it a lot easier to talk about a lot of things in projective geometry. You see, one of the main things in projective geometry is that you're often talking about triangles. And when you're talking about triangles, often you're insisting that your 3 points should not be collinear. Or when you're talking about quadrangles, you're often insisting a quadrangle is a set of 4 points. and you're often insisting that no three of those points are collinear, in order to stop these kind of degenerate cases occurring. Okay, so I've sort of generalized this concept. I say I've done it, I'm sure other people must have thought of this as well, but anyway, so I call it a set is nonlinear, so it's a set of elements of the same type. I say it's nonlinear when for every three distinct elements in that set, we have the A, B and C, we have the A dot B does not equal A dot C. So what do nonlinear sets look like? Well, here's one. Oh, and we use this nice kind of holy grail capital psi symbol here to represent the collection of all nonlinear sets with k elements of type M. Okay, so this is the set of all sets of this type that come from EM, which are basically having k distinct elements, and they satisfy this condition, which essentially forbids three distinct elements being collinear or concurrent if we're talking about lines. Anyway, let's get to some real examples. What about if we're talking about the case where I think I was normally using -1 to represent points. To be honest, since they're symmetric, I often get confused because it doesn't really matter. But anyway, let's say that M is -1. Let's say we're talking about points. And so this is let's suppose we have this set of three elements, distinct elements of course. Whenever I write things in curly brackets, I mean that they're distinct. I don't talk about multi-sets. And we're going to suppose this set is non-linear. That means that we're not going to have the, for elements A, B and C, we're not going to have the distinct elements A, B and C, we're not going to have that A dot B equals A dot C. Well, look, A dot B, that's this line here, and A dot C, that's this line here. Well, we don't want those two lines to be equal, right? Because we're trying to avoid collinearity, and this condition does that quite nicely. Similarly here, oh, and also, by the way, since a triangle is a self-dual object, really, the set of all triangles can be written as this or this. We could think of it because these are basically collections of nonlinear sets. I'm saying that they're actually collections of triangles. Now, the thing is that, say M equals -1, say we're talking about points, well, we're saying, okay, the set of all points, the set of all collections of three distinct, the set of all collections of size 3 nonlinear sets, and a size 3 nonlinear set is just a triangle, right? And similarly, we could think of it, if M equals 1, we're talking about lines, and again, this represents the set of all, the collection of all size 3 nonlinear sets of lines. Basically means the collection of all triples of distinct lines which are not concurrent, which is again a set of triangles. Anyway, what about this? What about this? This is a quadrangle. So this symbol here, I always liked psi ever since quantum mechanics. Anyway, this big capital psi here plays a big role in projective geometry because it represents, actually I better put a -1 there. Let's remember, -1, we'll use a convention that -1 represents points, if I can remember that. Well, okay, so what does this mean? Well, this is basically the set of all quadrangles, because a quadrangle is a set of 4 points, no 3 of which are collinear. In other words, it's a set of 4 elements from e to the m, where m is, let's say, -1 because we're talking about points, and it's a nonlinear set, so no 3 of its distinct elements have this property that they sort of have the same join or link or whatever. So that basically ensures that our set of 4 points is a proper quadrangle, and we can do all the complete quadrangle construction stuff that makes lots of nice things happen in projective geometry. Okay then, so one final gizmo before we get on to the actual axioms of projective geometry, of which there are 5. And that's basically what projections are. Kind of important to know, okay? So, a nice way to think of it is in terms of an elementary correspondence. So, here's a good way to think about an elementary correspondence intuitively. Okay, let's suppose that this is a point and this is a line. Now, on this blue pen here, let's suppose there's some dot, some point on the blue pen, some member of its range, some member of its neighbourhood. And imagine there's a dotted line which goes from that point, say here, up to this. In fact, why am I using another? That's daft. Here's a point. My pinched fingernails represent a point above, okay? And then there's going to be a line from this point up here which goes and meets this blue line down here, okay? And so in a sense, that sort of, let's imagine it's a dotted line linking this point on the pen to this point up here. That sort of puts those two things in correspondence, Now imagine instead that instead of just a single point up here, we have lots of lines emanating out from this point, and they're going to be rays of light, if you like, shining into all the different points on this line. That's basically what an elementary correspondence is. We put the set of points on the range of a line in one-to-one bijective correspondence with the lines going through a point, or the pencil of the point, if you like, or the rays going through the point. So, okay, let's look at it a little bit more algebraically now. We want to give a sort of line and point free definition of this notion of an elementary correspondence. To be honest, once we've defined elementary correspondence, it's easy to define what projectivity is, and then we're away, we're finished. We have all the tools we'll need. So basically, let's suppose for m equal to 1 or -1, let's say we've got an element alpha in e to the m, and we've got we've got an element beta in e to the minus m. So we have these two elements of different types. Now, the thing is that what we essentially want to do in this elementary correspondence is put the elements of the neighbourhood of this line. Well, for the sake of this example at the moment, I'll say that alpha's a line and beta's a point. Okay, they have to be elements of different types anyway. But right, so we want to put the members of the neighbourhood of alpha into a one-to-one onto correspondence. I sort of want to find a bijection from the members of this neighbourhood of alpha. We want to find a bijection from the neighbourhood of alpha to the neighbourhood of beta. So basically, we want to find mapping, a one-to-one mapping from the set of all points on alpha to the set of all lines through beta. Not only that, but we want this mapping to satisfy a certain condition. In particular, what we want to be the case is that when two elements are put into correspondence in this way, they are joined by an element of the opposite type to the type that they have. Okay? So in this example here, look, we've got a line, alpha, its neighbourhood has points, so we've got point x. Also, beta is the other big object that we're thinking about, and we're trying to put the neighbourhood of alpha into correspondence with the neighbourhood of beta, and so essentially we're trying to match up these points with these lines, but whenever we match up a point here with a line here, we want that line to actually join on to that point. Oh yes. Now, I've just remembered something. I think we also ought to insist that alpha shouldn't belong to the neighbourhood of beta. That's a kind of technical thing that we probably ought to add into our theory to stop certain pathologies happening. But I'm not going to talk about that too much now. You can ignore that I said that if you want. So basically, the thing is now, we've got our definition then. What's our definition algebraically? We're going to say that an elementary correspondence F is a bijection from the neighbourhood of alpha to the neighbourhood of beta, and it has this condition that I haven't written it down here. I haven't written it down. I better write it down somewhere. Hang on. Okay, so here's our really central crux of the matter. It's here. We want this condition to be satisfied. So we have a bijection from the neighbourhood of alpha to the neighbourhood of beta, but it must satisfy this condition that for every member of the neighbourhood of alpha, we want to have that if we have a look at the image of this x, this member of the neighbourhood of alpha, which is called x, if we have a look at the image of x, which is called f of x, that's where x gets mapped to under this elementary correspondence, well, let's have a look at the neighbourhood of that, whatever that may be. Well, we're going to insist that that has to have a non-empty intersection with the neighbourhood of beta. So in other words, okay, it's much easier to see by the diagram, okay? Here's our line alpha. We're mapping points on alpha to lines going through beta, okay? And what we want then is we want the line Okay, so now we get to the meat of projective geometry, which, as the astute of you may have guessed, is projections. Well, to define projections, we start with something elementary. The elementary correspondence, okay? So, just for a while, I'm going to think about it in the familiar language of points and lines, okay? So let's suppose we've got a line called alpha, and this line has a neighbourhood, so it has a load of points on it. Little x is one of those points. And we also have, in addition to this line alpha, we have a point beta, okay? And beta also has a neighbourhood. Beta has a load of lines going through it. Now, an elementary correspondence is when we do a one-to-one mapping from the neighbourhood, say, of alpha to the neighbourhood of beta. In other words, we put the points on this line in correspondence with the lines that go through this point. But the crucial thing is we do it in such a way that when we put a point on this line in correspondence with a line through this point, the line through the point has to join beta with the appropriate member of with x, with the appropriate member of the neighbourhood of the line. You got that? So basically, a nice way to think of it is, imagine you've got a load of points spaced along this line, and then there's kind of like a beam flashlight comes along, and it puts these points on this line in one-to-one correspondence with lines emanating from this spotlight, which would, beta would be the point where that light was coming from, or whatever. So that's the kind of geometric interpretation. Now let's get algebraic. Here's my definition of elementary correspondences, which doesn't talk about points and lines. Okay? So here's the deal. Suppose we've got an element alpha in EM. We've also got an element beta in E minus M. So alpha and beta are elements of different types. One of them's a point, one of them's a line. Okay? And F is our elementary correspondence. Now it's a bijection, a one-to-one onto mapping, from the neighbourhood of alpha to the neighbourhood of beta. Moreover, we have this important property. This is the real crucial property. It is that for every element in the neighbourhood of alpha, we have to have that. So say we've got this element x in the neighbourhood of alpha, we have to have that the neighbourhood of that point, of that element x, has to intersect with the neighbourhood of the image of that element x. In other words, there has to be something which lies within both the neighbourhood of x and the neighbourhood of x's image. So if we go back to our physical picture, this might seem a bit more sensible. In this case here, look, we've got this element x, which is in the neighbourhood of alpha, and the neighbourhood of this contains this line here, okay? And also, Okay, so here's the algebraic definition of our elementary correspondence. We want to, well, we have an element alpha, which is in this set EM, and we have an element beta, which is in the set E minus M. So alpha and beta are of different types. One's a point, one's a line, we could say. And an elementary correspondence, well, that's a bijection, a one-to-one onto mapping, from the neighbourhood of alpha to the neighbourhood of beta. Now, it has to satisfy one crucial condition, and that is that for every member of the neighbourhood of alpha, in other words, for every element that this mapping F is acting upon, we have to have this condition that the neighbourhood of beta intersects with the neighbourhood of the image of the point we are acting upon. So this might seem a little cryptic. Let me try and convince you of it here. Okay? Here is our element x, and we want to do one of these elementary correspondences. Now, basically, we want to insist then that this point is going to be put into correspondence with the line that goes through it and goes up to this point beta. And that line we've called y here. And you can see that that line does indeed belong to the neighbourhood of x, because of course it has to go through x, and it also has to belong to the neighbourhood of beta. So provided that there is some element which belongs to Okay, so here's the critical idea then of the elementary correspondence. Basically, we want to have, let's say we have an element alpha belonging to a set EM, and we also have an element beta belonging to the set E minus M. So alpha and beta are different types of things. Maybe alpha is a line and beta is a point or something. And we'll also have this extra little stipulation that alpha shouldn't be in the neighbourhood of beta. We won't talk about that too much now. That's just to stop some certain pathologies that can happen. Maybe you can think about why that's a good idea to have that restriction. Anyway, so what's an elementary correspondence? Well, it's just a bijection from the neighbourhood of alpha to the neighbourhood of beta, which has a certain special property. And that special property is simply that for every member of the neighbourhood of alpha, we have so every member x of the neighbourhood of alpha, we have this join or meet or whatever you want to call it, x dot beta, that's actually got to be equal to the image of x under this mapping, which so is called the elementary correspondence. So in picture form, we've got something a bit like this. Say alpha's a line and beta's a point. Well, we've got this line alpha, we've got a range of points, a neighbourhood. X is a member of that neighbourhood. It's a point on this line, and we have this elementary correspondence which is mapping these points on this line to these lines through this point, the neighbourhood of beta. And it has to do it in such a way that whenever a member of the neighbourhood of alpha gets sent to a memberhood of the neighbourhood of beta, it has to do it in such a way that the objects that you get linking the original element and its image sort of joins those two things together. That's what an elementary correspondence is. A nice kind of physical picture of it in this case, imagine like a 2D picture where you've got like a line with a load of points, say equally spaced or something, and you have like a flashlight at a point here, and it kind of swings round in a circle. So it's putting these things in one-to-one correspondence in such a way that there's a beam of light which is connecting every point on the range to the place where the flashlight's emanating from. Or if you like, you can think of the beams of light as members of the pencil of the point. But we don't need to talk about pencils anymore because we can get rid of all that. Now, what about projectivities? Well, now we've defined what an elementary correspondence is, it's quite easy to define what a projectivity is. Basically, a projectivity is just a composition of perspectivities. Okay? So I'm using this notation here, and it looks a bit scary, but I'm using this to represent the set of all projectivities. Have to excuse me, I have a bit of dyslexia or something, and I often say perspectivity when I should say projectivity. In this talk, I only want to say projectivity if I can help it. So we have this projectivity which sends with projectivity called F, okay? And it's a projectivity from some element alpha 1 to some element beta 2. Okay, so what's it look like? Well, like in elementary correspondence, it's a mapping from the neighbourhood of alpha 1 to the neighbourhood of beta 2. What is it though? Well, it's just a product of elementary correspondences, or a composition of elementary correspondences, or a sequence of elementary correspondences. So it looks a bit like this. We start with alpha 1, maybe that could be a line. Then we have an elementary correspondence which goes from alpha 1 to this point beta 1. Then we have another elementary correspondence which goes from this point beta 1 to this line x2. Then we have another elementary correspondence which goes from this line alpha 2 to this point beta 2. I'll just hold that up for you so you can study it for a while, and you can see that the if you look at this down here, you can see that the this projectivity, or projection as it's sometimes called for short by me, is basically just a it's just a composition of elementary correspondences, and basically projective geometry is all about what kinds of properties are left invariant under these kinds of projections. And so I think we're done. I think we have all of the tools under our belt that we need now to lay out the axioms of projective geometry. So I did a course on YouTube a little while ago, or I'm still doing, I suppose, if I can be bothered to make any more videos for it, which I probably can. And it's called The Foundations of Projective Geometry. And I used 5 axioms, which I sort of squeezed out of Coxter's lovely book on projective geometry. And I'll read them to you. These are just for the projective plane, 2D projective plane. Okay? Here they are. Number 1. 2 distinct lines meet at least 1 point. Number 2. There are 4 points, no 3 of which are collinear. Axiom 3. The diagonal points of a quadrangles, triangles are not collinear. So that involves something to do with complete quadrangles, which, if you haven't heard of, don't worry, because I'll explain it in a bit. Axiom 4 is basically Desargs Theorem, that if 2 triangles is a perspective from a point, then they shall be perspective from a line. Again, I'll talk about that in due course. Finally, any if we have a projectivity from a line to itself, and that leaves 3 distinct points invariant, then it has to leave everything invariant. It has to be the identity mapping. So in other words, if some projectivity doesn't move 3 different points, then it doesn't move any of the points on the line. Okay then, there are axioms. Now let's see how we can express them using all of this algebraic machinery that we've just been unrolling. Well, axiom 1, that's fairly easy. Axiom 1, basically all we have to say is that if we have a couple of elements, alpha and beta, one's in EM, one's in E minus M, so they're of different types. Well, alpha dot beta has to, sorry, I said that wrong. To get axiom 1 says 2 distinct lines meet at one point. Well, we can just say that 2 elements of the same type have this kind of dot operation which forms an element of the opposite type. So if we have alpha and beta belonging to the set EM, then alpha dot beta belongs to the set E minus M. For example, alpha and beta might be lines, and then alpha dot beta is a point. Okay, so that's our first axiom done with. Axiom 2 is quite nice. Axiom 2 basically says that quadrangles exist. It says that sometimes you can have 4 points and no 3 of them are collinear. Well, we can write it like this. It's quite nice, because this is the set of all quadrangles, all nonlinear sets with 4 elements, which have points, because m's minus 1. And this is the set of all quadrilaterals, the set of all nonlinear sets from E1, which have 4 elements. So basically, this is the set of all quadrangles, this is the set of all quadrilaterals, and this says that neither of these 2 sets are empty. So we have some quadrangles and we have some quadrilaterals. So that gives us our axiom number 2. Axiom number 3, the diagonal points of a quadrangle's triangles are not collinear. Okay. Right, so what are the diagonal points of a quadrilateral? I should tell you this. If I can. Oh, I seem to be drawing a lot of quadrilaterals today. Okay then, so axiom 3 then is concerned essentially with quadrilaterals in the standard setting. It says that the 3 diagonal points of a quadrilateral won't be collinear. So I better get you up to speed on that before I give you the new algebraic way of saying it. So a quadrilateral is just where you have 4 points. I'm calling them x1, x2, x3 and x4. And they've got to be placed around the plane, projective plane somewhere, so that no 3 of them are collinear. And then if you draw all the 6 possible lines which connect pairs of those points, you'll find that if you look at where those points are, those points will meet at some extra... Sorry, if you look at where those lines between... Let me start again. You draw all the 6 possible lines between these 4 points of your quadrilateral. And if you look at the lines, you'll notice that there will be 3 extra points formed by the intersections of those lines, in addition to the initial 4 vertices you started with. Those new 3 vertices, in particular in this case, this one here, the circled ones, this one here, and this one here, they're called the diagonal points, or sometimes they're called the diagonal triangle of the quadrilateral, of the quadrangle. And our axiom number 3, basically states that the so-called diagonal triangle associated with a quadrilateral is never a straight, it's never collinear, it's never a straight, these 3 points are never lying up on the same line. They always form a proper triangle. Okay, so how do we state this algebraically? Well, it turns out to be somewhat simpler in a way. Basically, all we have to do is say, well, let's pick m to be either -1 or 1. Now, if we take one of these stable sets, nonlinear sets, yeah, anyway, I don't know if I've said stable sets before. I always mean nonlinear sets. Yeah, so nonlinear sets, x1, x2, x3, x4. So it's a nonlinear set with 4 elements in it. We won't worry too much about whether these elements are points or lines, since everything's symmetric anyway. But to satisfy axiom 3, what we want to insist is that these 3 diagonal elements, which can be formed, if you take another look at this picture, if you want to pause it and think about it, I'll try and put these next to each other. You should be able to see that these 3 circled points are described algebraically using this kind of joining notation that I've used. So essentially what this is saying here is that these 3 diagonal elements are not going to lie in a straight line, or if lines, then they're not going to be concurrents. In other words, they're not going to form a a nonlinear set of 3 elements. You must excuse me, I seem to be getting some kind of dyspraxia or dyslexia. It's getting worse recently. Quadrangles, quadrilaterals, stable sets, nonlinear sets. I often get these words juxtaposed. I apologise. Okay then, so that's it. Now let's get on to the next axiom. Axiom number 4 is the biggie. This is basically Desargs Theorem. Desargs' famous theorem, which pretty much reinvigorated projective geometry. His statement that if 2 triangles are perspective from a point, then they're perspective from a line. That's basically what our 4th axiom is. And so basically it is a little more complicated actually to state this in our new language, but at least we're treating points and lines symmetrically. So here we go. Well, okay, firstly let me recap you about what Desargs' theorem says. It says that if you've got a triangle like this one here with vertices A, B and C, and you've got another triangle like this one here with edges A dash, B dash and C dash, well, if those 2 triangles are perspective from a point theta, in the sense that if we draw rays through corresponding vertices that go through theta, then they all meet at this point theta. So it's kind of like if you eye these triangles at theta and look at them, then vertex little a lines up with the vertex opposite edge capital A dash in this other triangle, and similarly little b lines up with the vertex opposite big B dash, and so forth. So you can see that these 2 triangles are perspective from theta in this sense, and Desargs' so-called theorem, which we actually have to take as an axiom, it just turns out that you can't prove it from the other axioms that we want to use. So we're going to take this as an axiom. Anyway, the claim is that if we have these two triangles perspective from a point, then they must also be perspective from a line. In our case, here in this picture, the line is labelled capital X. What does that mean? Well, it means that if you join corresponding edges up, say you join this edge AB in the first triangle with the edge C dash, which corresponds to it in the second triangle, well, they're going to meet at a point. And similarly, if you join this edge of this first triangle, AC, with the corresponding edge B dash of the second triangle, that'll also meet at a point. And also, finally, if you join the last pair of corresponding edges, they also meet at a point. And Desargs Theorem claims that those 3 points always lie upon a straight line. Therefore, the snappy way to say his theorem is, if two triangles are perspective from a point, then they're perspective from a line. Okay? How do we state this? Well, we can do it using our notion of nonlinear sets. Okay? So we have a nonlinear set of free elements of some type M. So we won't worry about whether it's points or lines. We'll call the elements in that set A, B, and C. And we'll have another nonlinear set of free elements of the opposite type. So it belongs to e to the minus m. And we'll call the elements of that A dash, B dash, and C dash. And then basically, we just draw it out like this. Let me just hold this up to the camera. Just maybe you want to pause it and think about it for a second. So for example, what does this say here? It's A dot B dash C dash. So what's little a dot big B dash big C dash? Well, little a is the vertex of that first triangle, and big B dash big C dash is the edge. Hang on. Sorry, yes. Big B is there. It's this edge, and big C is this edge. And so big C, big B, big C, that's the join of these two edges. So it's the vertex of this second triangle, which is opposite the edge big A. So essentially what this is saying here is that we have vertex little a from the first triangle and the vertex opposite big A dash in the second triangle. And similarly we have vertex little b and the edge big B opposite it. Sorry, the vertex opposite big B, and we have vertex little c and the vertex opposite edge big C. And what this statement is saying here is that basically this is a line, okay? This is a line which joins this vertex A of our first triangle to this vertex big B, big C dash of our second triangle. So that's one of these lines through corresponding vertices, as is this and as is this. So what this is basically saying is that we have these three lines through the corresponding vertices, and our claim is that they belong to the neighbourhood of theta, as they should. Theta is supposed to be the point where all these lines meet, and it's of type M. And sort of similarly, we want to have this kind of dualistic statement here. which basically says that the corresponding lines meet at 3 points on X. So that's one way of saying Desargs Theorem, which we are going to be using as an axiom. Now, that's the first 4 axioms done. One more to go. It's quite easy. Go back to this notation. We'll let in big P alpha beta denote the set of all projectivities from the neighbourhood of alpha to the neighbourhood of beta. Well, basically our final result, which is essentially that if we have a one-dimensional projectivity from a line to itself, if it has 3 invariant points, then it's the identity. Well, it's quite easy to write that. Basically, if we have... Oh, that shouldn't be there. We write it like this, okay? So, if we've got a set of 3 points, obviously they're distinct points because they're in curly brackets, if they're in the neighbourhood of alpha, and we have this projectivity, any projectivity that sends this one-dimensional form alpha to itself, well, if the projectivity maps this point A to itself, and if it maps B to itself, and if it maps C to itself, then it maps every single point on the line to itself. It does so, it does so for every member of the neighbourhood of alpha. So that's it. That's all of the sort of foundations of projective geometry. On my website, I've got a one-page scribbling which has all this on it. So I'm trying to sort of condense it all down into the smallest possible form. Maybe try and take out all the words, maybe bung it in a computer and see if we can do some automatic proving, or try and find some new patterns in some different places. If you're interested in this kind of stuff, send me an email. I'm always happy to collaborate on stuff like this kind of research. And just want to re-emphasize, projective geometry is a new game for me, so there's probably some experts out there who've been doing this for like 20 years who are thinking, oh my god, who is this guy? Everyone knows that, or whatever. But hey, that's the way I learn stuff, by investigating it for myself. So thanks for your attention.